Hello everyone, my name is Setu Gupta. I'm a BTech 2018 ECE student and this is my submission for homework for bonus. So in this video I'm going to be talking about optimizing addition operations and in general other associative operations. So what is the problem? Well, the problem is we want more parallelism. The more parallelism I have, the faster I can execute my code. Now the problem is that sequential addition is very slow. Why is it slow? Because it requires order of n sequential operations, where n is the length of vector to accumulate over. So the naive sequential addition has data dependencies, to be precise the read after write dependencies. To understand this point, let's take an example. Suppose we want to compute a plus b plus c plus d. The naive implementation might use a cumulative variable, let's say temp, and the computations will happen in such a form. The step 1 would be to add a plus b and store it in temp. Step 2 would be to add c to the temp variable, and the step 3 would be to add d to the temp variable. Now this type of addition is not very optimal, because you can see step 2 cannot start before step 1 completes. Note that the data dependencies are shown in red color, and you can see that step 2 requires the updated value of temp generated by step 1 to start its computation. As a result, we force a sequential order on the number on the operations of 1, 2 and 3. So let's take an example to see how this works. So let's say we have two arrays of length 8, let's say a and b, and we want to apply a multiply and accumulate operation on these arrays. This is a very common operation which is used in various signal processing applications, and hence I chose this example to show you the problem. So the first step would be to do the addition. Next we perform the addition. Now note that the problem over here is that the output of this addition has to feed to an adder whose first input is coming from here and the second input is coming from here. But at the second cycle, the output of this adder is not ready. Hence this particular multiplier will have to wait for one cycle. Similarly, this will have to wait for 2 cycles, and so on and so forth. So we see at the next cycle, the output of this can be now finally be read because this output is ready. Similarly, the next cycle, the output of this can be read because this is ready, and so on and so forth. And so we see that we required 7 cycles to reach the result. Why 7? 1, 2, 3, 4, 5, 6 and 7. We reached 7 sequential addition cycles, and we can see how this is order of n because we required n minus 1 cycles, where n is 8 over here. So n minus 1, that is 7. We require 7 cycles to compute this addition. We have 7 sequential operations, i.e. order of n. So can we do better? Yes, we can. So how can we do better? Well, we can exploit the associativity of addition operation. Now what is associativity? The associativity is a simple property of binary operators which different operators such as multiplication, addition, the maximum operator, the minimum operators have, which states that the order in which the operations are carried out on the operands does not matter. For example, whether we add a plus b first and then add to c, or we add b plus c and then add to a, the result is going to be same regardless. So the order does not matter. So how can we use this to exploit parallelism? Well, we use a binary tree for addition. We will see this pictorially why we are calling this a binary tree. But before we get to that, let's look at the motivation. Well, the motivation is that in a binary tree sort of addition, we will only need order of log base to n sequential operations. Now this is a huge improvement over n, because as the n increases, I only have to pay the cost in a logarithmic scale. Also, note that the total additions which I am performing is still order of n, because at the end I have to do the same amount of work. The only thing that I am doing is I am scheduling it in such a way that I can do more work in parallel. Also, this approach allows us to do more efficient exploitation of parallel load operations when available. So let's take an example of optimized case, and we'll see why I have used the word binary tree addition over there. So let's again take the example. We have two vectors of length 8 and we are doing a multiply and accumulator operation. So the first step would be to do the multiplication operation. The second, now recall that in the naive implementation, the next step would have been to add the values of these two multiplier units, and then wait till the addition of these two are complete, and then use the value of this multiplier. But now let's see what we are going to do in this step. In this case, we are actually consuming the output of all the 8 multipliers instantaneously by 4 different adders. Now, why we were to do this in parallel? Well, because this adder only depends on values of these two multipliers, this depends on only these two multipliers, and so on and so forth. As a result, I can consume values of all these multipliers in the next cycle. Next, I again use two adders to combine the result of these two and these two. Similarly, I again use a single adder to combine the result of these two. As you can see, this structure represents a binary tree with this as the root and these as the leaves. Note that we are required only 3 iterations, that is log base 2 of 8 is 3. That's why we required 3 iterations. And we were able to consume the values of all particular level of a tree in the very subsequent cycle. And finally, after 3 cycle latency, we can generate the result. So now let's look at the pipelining implementations of both the naive as well as the optimization approach. So in the naive approach, we need to buffer later multiplication stages till the previous stage is complete. As we saw in the earlier slides, that the later multiplications had to wait before the output could be consumed because the previous multiplication didn't finish the addition operations. So we need to add increasing number of buffers as we move from left to right to ensure correct pipelining. In total, we will need 1 plus 2 plus 3 till n minus 1 plus n minus 2 buffers, and we will see where these numbers are coming from in the next slide. The main takeaway from this slide is that we will need order of n square buffers. That means as the length of n increases linearly, the number of buffers will increase quadratically. We see that the latency for naive implementation is order of n, and precisely it is n minus 1. So let's look at how a naive multiply accumulator operation would happen. Now in this example, I have considered arrays of length 4 just because to save the screen space, but the same analysis can be done for larger vectors as well, and we can verify a hypothesis that the order of the operations is order of the buffers is n square, as well as the latency is order of n. So the first step is to do the multiplication. The data is read from these two arrays and it's multiplied and stored into these flip-flops. The blue rectangles represent flip-flops. In the next cycle, the data from these flip-flops goes into the next flip-flops, as well as the data from these flip-flops move into an adder, and the adder will compute the value and store the data in this flip-flop. Note that at this stage, the data at this flip-flop and this flip-flop is ready to be read for the next adder. The next adder reads the values and compute it and stores the value into this flip-flop. Similarly, the data now flows till this flip-flop, and we can see that now we have data ready in this flip-flop as well as this flip-flop, and hence we can do one more addition and we can store the result. As we saw, for a vector of length 4, we needed 3 operations and we had a latency of 3. Why? We can calculate the number of flip-flops from any input path to any output path. We can see this is 1, 2, 3, similarly 1, 2, 3, similarly we can do 1, 2, 3 and 1, 2, 3. That means we have a latency of 3. Also, the number of buffers we needed is going to be 1. So this is the first multiplier. Then we are going to need increasing number of buffers. So this is your 1 plus this would be 2, this would be 3, this would be 1 plus 2 plus till n minus 1. Here n is 4, so we are only going till 3. So this is where the first term, that is 1, is coming. This is where the second term, that is summation from 1 to n minus 1, is coming. The third term is coming because of these buffers. As we can see, if we have n vectors and n length vector, that means we will have n minus 1 addition operations, and for n minus 1 addition operations we will need n minus 2 buffers, because we will need to place a buffer between any two consecutive additions. Hence we get this n minus 2, and overall we get a order of n square number of buffers needed. Now, pipelining issues with optimized implementation. So now let's look at the optimized implementation now. Now each added stage needs to be buffered, and as a result, this allows us to easily exploit the parallel loads. The number of buffers which we will need is 2 plus 4 plus 8 plus and so on and so forth until we reach n. So the last stage is going to need 2 buffers, and the subsequent stages are going to need 4 and consequently up till n. So the number of stages that we have is log base to n. And now notice that this number might seem a bit larger than the previous computation, but note that the number of terms in this series is going to only be CL of log base to n, and it turns out that the number of buffers which I need is significantly lower in this case. So for the sake of simplicity, let's assume that n is exact power of 2. That means the number of stages would be p, because log base 2 of 2 to the power p would be p, and CL of any integer is integer itself. Hence we have p stages. Now if we compute the sum of this geometric series with number of terms by putting number of terms as p, we find out that we will need total of 2 into 2 to the power p minus 1 buffers, and replacing 2 to the power p by n, we get 2 into n minus 1 buffers. That means we will only need order of n buffers. Recall that the naive implementation calls for order of n square buffers. Also note that the latency for this type of structure is again order of log base 2 n. Why? Because the stages are only p, where p is nothing but log base 2 n. So let's look at the optimization approach pipeline. So again we start with two vectors of length 4 each. The first step would be to do a multiply operation. The second step would be to accumulate the data of these two multipliers and these two multipliers. Again, this can be done independently because this depends on only these two data and this depends on these two data, hence both the additions are independent. Similarly, we again accumulate and store the result. Note that we only needed latency of 2 cycles because we can say 1 and 2, similarly 1 and 2, and we can see that the number of buffers we needed was 2 plus 4, that is 6, and as we predicted it would be 2 into n minus 1, that is 2 into 3, that is 6. Alright, so and again, as we said, we have four number of elements in an array, and we can see that log base 2 of 4 is 2, that's why we required 2 cycles. So now let's look at convolution example. So how would we convolute? Well, each element of the output array can be computed parallelly, and each element's computation is nothing but a multiply accumulator operation. So suppose the weights of the convolution is stored in one array, and the other array is pushed is right shifted at every cycle, and at every cycle I'm computing the multiply and accumulator operation of these two arrays, and using the architecture just discussed in the previous slide of parallel addition using binary trees, we can do this operation in a very quick fashion. So now let's talk about what is the support from the HLS tool which we are using. Well, the HLS seems to be able to infer the optimized additions for AP uint 16 types, and I also tried it for AP int 16 as well as int 32, the normal 32-bit integer. The HLS tool was able to infer this type of binary addition, and it was able to automatically generate the circuit for it. However, the tool was not able to infer the possibility of such a solution for floating point data values. Hence, we will need to force this optimized addition in the floating values. You can refer to the code uploaded along with the other material to see how this is forced, but the gist of it is that we will have to explicitly write multiple loops. One loop would be will convert 32 elements into 16 elements and 16 to 8 and so on and so forth, and each of these loops would have to be unrolled. So let's look at what kind of latencies which you can achieve. So first let's look at the naive implementation. We see that the iteration latency is 167. The reason it is 167 is because all the additions are happening sequentially. As a result, the latency of this loop increases, and we have to pay the penalty in number of total latency of our block. Also notice that the flip-flop required are around 26,897, and we can now compare this with the optimized implementation in which the latency is considerably lower of only 46, and we find out that the total latency of our IP has also decreased from 400 to 90. This is a very big improvement in our code, and almost 4 times improvement, and this would only increase as we increase the length of the vectors. Over here the computation is done for only 16 length vectors. As we move towards larger length of vectors, the improvement would be even higher. Also note that the number of flip-flops required is less at only 22,000. Now let's look at the timing diagram generated by the HLS analysis tool to see how the additions are happening. So we can see that we have 8 additions, we have 16 additions here, then we have 8, then 4, then 2 and 1 as we predicted, and we can see that all these additions can be done parallelly, then these can be done parallelly, and so on and so forth. So let's generalize this to a more number of operators. So this approach is not limited to additions. Actually, this can be replaced by any binary operator which is associative, and examples include multiply, max and min, and etc. Also, we don't have to necessarily restrict ourselves to binary operators. We can go up to ternary operators and even higher order operators. However, the only thing we need to keep into mind is that all the computations regarding the buffer complexity as well as the latency complexity will have to be changed from log base 2 to log base O, where O is the order of the operator. So that's all from my side. Thank you.